Hi all, welcome back to Environmental Science 101. For this portion of lectures, we're going to talk about energy and matter. And so you might be familiar with some of these concepts, but it's just an overview of kind of the cycles of energy. And the importance of this is really, if we're going to talk about the environment or talk about situations with the environment, whether that be pollution, climate change, our involvement in the environment through endangered species or inhabiting certain places, the use of fossil fuels, all of this, really you have to know the conversion, or at least components of the conversion of energy, and what makes up the components of the planet. It's been known for a very, very long time, even before we knew the processes at which, say, photosynthesis worked. It was known that the sun is the driver of all of life. Without the sun, without that constant bombardment of photons and that free energy, so we can think of the sun as this free energy sending photons to the planet, and without that, we have no life. There's nothing on the planet. And Galileo noticed that. I mean, many individuals in pre-industrial times realized that the sun was the key to development on this planet, not some ancient fossil fuels which are finite and non-reusable, and if you use them you have to wait 300 million years to get them back. I mean, it takes a very long time for plant material to be converted back into a fossil fuel, and it really takes perfect conditions for this to occur. In many cases it might not occur at all, right? That's why we find pockets on our planet of different fossil fuels, and it's not just all on a single layer everywhere, because you have to have the right conditions. You don't have to have the right conditions for sun. The sun is there. And Galileo knows this. Lots of philosophers knew this at the time. Okay, so we're going to talk about kind of that component and the importance of understanding where the energy comes from and how it cycles on the planet. First, I want to ask you guys a question, and then I'm going to talk about studies that have been done before to support a hypothesis or refute a hypothesis. For a long time, there have been hypotheses on what makes up the mass of this. Okay, so someone gives you a round slab of wood, okay, whether that be firewood or, like this is, and they ask you this question: what makes up the majority of the mass of this item? Okay? This has been asked of intelligent people for a very long time, and the answer is super simple, but often the answer given is incorrect. Okay? So this was asked of Harvard science grads about 10 or 15 years ago, and it's probably been asked of lots of other grads. It's a common thing for people trying to assess whether or not students are getting concepts that they should have learned in undergrad beginning science courses. Do they retain them after they graduate with a bachelor's degree in science? And so lots of teaching science or education instructors will ask this question, along with other things like, tell me about how planets move around the sun, or does the sun move around the planets? What causes seasonality? There's all kinds of things, questions that are asked of science grads, just to see if they know these simple concepts. They might be able to tell you, how proteins work or how a gene is copied and things like that. But do they know simple things like what makes up the majority of the mass of a block of wood? Well, when this was posed roughly 10, 15 years ago to science grads, this is what they said. 75% of the science grads, Harvard science grads, said it was water. Okay, that this is water. Or the majority of the mass of that is water. 15% said it's carbon, and 10% said it was minerals from the soil. Okay. And so this is a testable hypothesis. Right? It's been a testable hypothesis for hundreds of years. Okay? We always wanted to know the growth of plants. We've known for a very, very long time that you can take something as simple as an acorn that might have a mass of 3 to 4 grams, okay, plant it in the ground, wait 50 years, and now that organism weighs 8 tons. Okay? What is the source of the increase of matter in that plant? Where is that mass coming from? Okay? Another example that's often presented to undergraduate students is a redwood tree, the biggest tree in the world, produces roughly 1 million seeds. Those 1 million seeds weigh about 8 pounds, so a single seed weighs about 0.003 grams or so. And you take that 0.003 grams, and a couple hundred years later, we're talking, 50,000 pounds or 25 tons of a conversion. Where does that mass come from? Classic experiment. Okay? This classic experiment called the willow tree experiment. Okay, and we'll go through and talk about what John Baptist did. But the initial hypothesis was John Baptist in the 17th century had an idea, had a hypothesis that you have these giant trees growing. They come from very small seeds, that the plants must be gaining the mass of the tree through the roots. Okay, so the soil around these trees must be getting lighter or having less minerals, less nutrients, and that's what the tree is building itself off of. Okay, so the initial hypothesis was that the majority of plant mass is from soil nutrients. Okay, testable. Okay? And it really wasn't attempted until John Baptist Van Helmont, Helmont came up with a hypothesis and a test to decide this. And that came in the 17th century by this individual, John Baptist. Okay, he was a chemist, he was a physiologist, a physician, so he's a doctor. He got his medical degree in 1599. He practiced medicine, but he also was a scientist and practiced kind of the natural sciences. He liked to hypothesize what causes things, like what causes the mass of a tree to change, what causes proteins to react to certain things. Okay, and so he kind of had his hands and fingers in all kinds of little projects. He is known as the founder of pneumatic chemistry, so he is the founder of the chemistry of gases, and most likely, based on all the writings and notes, he was the first person to describe how enzymes worked. But it was just superficially. Like, we didn't really know what proteins were made out of. We didn't know that they were made out of amino acids, or much like that. But he did describe the process by which enzymes are kind of like a lock and key mechanism, and that things would interact with them and they would help break down things or build things. So real superficial, but describe the first kind of how enzymes work. And from a environmental science perspective, or from a transfer of energy perspective, he came up with the classic willow tree experiment, okay, to try to decipher whether or not the majority of a tree's mass is coming from the soil or something else. Okay, so his experiment was really just that. He hypothesized that trees don't gain the mass from the soil alone, but it also comes from the air. And so he set up an experiment where he planted willow trees in pots of dry soil. Simple project. And it's surprising to many that it took, hundreds of years for someone to come up with a project to test this out. But again, it's also surprising to many people to see what the answer to what is the majority of the mass of this object is. For students who are supposedly going to the best school in the country, and to see what their answers are. Okay, so he planted a willow tree sapling in a pot of dry soil, just like this. Okay, he weighed the tree, the sapling, and he weighed the soil. Okay, so both masses were recorded. He had a watering schedule. He regularly watered them, and he weighed the water that he put in the pot at all times. Okay, after 5 years, the willow tree gained 74.5 kilograms of mass. So, his hypothesis, if it's supported that trees don't gain mass from the soil alone, but also from the air, then you would expect that this is not a one-for-one. The soil shouldn't weigh around 20 kilograms, and the tree now weighs 74 kilograms. So the soil shouldn't have lost 20 kilograms. And indeed, the soil did not. Okay, the soil only lost 0.06 kilograms of mass. And most people contribute this to potentially water differences. Okay, differences in the amount of water and evaporation and kind of a grow period. So the soil itself only lost 0.6 kilograms of mass. So his original hypothesis was rejected. Okay? That indeed the tree mass is not coming from the soil. Okay? So it brings me back to this question. And we'll talk about this, and I'll probably ask you this question again at the end of the quarter. What makes up the majority of the mass of this item? Okay. Are the Harvard science grads right? Is it water? Is, indeed the majority of this mass of this object just water? Is it carbon? Where's that carbon coming from? Is it minerals from the soil? I think we know that based on John Baptist's work that it's not this. Okay? And indeed, when we look at the answer is that it's carbon. Okay? Carbon makes up about 50% of a block of wood. And a freshly cut chunk of wood, okay, it might be 25% water. Okay? But a block of wood like this, firewood, which is dried and ready to be burned, it's probably closer to 0%. So carbon itself makes up 55% of this. Other things that make up this block of wood are oxygen and hydrogen. Okay? And we know this because all we have to think about is, what's the process of photosynthesis? Okay? What's the purpose of photosynthesis? It's for a tree, a plant, to absorb sunlight, utilize carbon dioxide from the air, water from the soil, mix them together, and produce carbohydrates. And those carbohydrates can be complex carbohydrates and be in the form of cellulose, which is a complex carbohydrate that makes up wood fiber or wood grains. Okay? And that, indeed, is what makes up the block of wood. Yes, water is stored in here, but in a block of wood that's dry, there's no water. But the carbon is still there. And if you logically think about this, if the majority of this, the mass of this object is water, then could you burn it? Highly unlikely. Okay? So even at 20% water, if this is freshly cut, it's going to be very difficult to burn that block of wood. Okay? But if it's a piece of dry wood, okay, that carbon will ignite. Okay, you'll break the bonds using fire and gain energy or release energy from those bonds. And those bonds are going to be that carbon, hydrogen, oxygen bonds that we find in carbohydrates. Okay? And most people, you don't have to go to Harvard to know this. And actually, in fact, all Harvard science grads know this. Okay? It's just when you're put on the spot, you revert back to maybe a prior knowledge of people saying, well, organisms are 90% water. Okay? Well, this is not true. They're not 90% water. Okay? 25% water, freshly cut wood. Okay? We're, roughly 70% water, maybe 70% water. Okay? But the idea is that that's not the mass of a tree. That's not where the mass of a tree is coming from. It's not water. Okay? The mass of the tree is coming from carbon. And that carbon, the cool thing about it, is coming from the atmosphere. This is why trees, forests, and really all plants are called carbon sinks. Because they're taking carbon dioxide and they're fixing it in their tissue. And then they hold that carbon in their tissue. And this is why things like forest fires and logging operations and things like that can release lots of carbon back into the atmosphere, is because all these carbon sinks, when you start removing them from the landscape, that carbon is now able to be released back into the atmosphere. Okay? And we'll come back and we'll talk about some other biologists or scientists that talked about this process and really kind of paved the way for figuring out photosynthesis. Next time.